Right. Hello everyone, I am Srisha. I am from CSE AML Department of Section D. Today's my mathematics and calculus topic is of Tech Talk, cylindrical coordinate transformation. So let us move on to the topic. So first, a brief notes on cylindrical coordinate transformation. So first, let us know about what are cylindrical coordinates. Cylindrical coordinates, let us consider like r, theta, and z, are used when problem has circular or rotational symmetry, such as flow in pipes, jets, and rotating machinery. Uh, there is a relationship to Cartesian plane like x, y, z. So not only in pipes, jets, and rotating machinery, but also we'll use in different areas of the cylindrical coordinates. So this is the such an important topic we have. So now let us relate this r, theta, z coordinates to the Cartesian coordinates. Like x is equals to r cos theta and y is equals to r sin theta, z is equals to z. These are the parameters, and we all know that r is equals to under root x square plus y square. This is the formula. Then theta will become tan inverse of y plus x. So actually this occurs with by using the Pythagoras theorem, by having an x-axis, y-axis, and hypotenuse. And here x-axis acts as cos theta, y-axis acts as sin theta. So here r is nothing but a perpendicular to it. So its components are become r cos theta and r sin theta. Next, we have velocity components in cylindrical coordinates. So the velocity vector becomes v is equals to vr er plus v theta e theta plus vz ez, where vr is a radical component, v theta is equals to tangential shift component, vz is axial component. So we all know that vector is nothing but adding any two vectors, resultant vector. This is the resultant vector. Uh, Next we are going to. So now we are going to continuity equation of incompressible flow. So this is our, let us, now here we have a differentiation, that is 1 by r, 1 by r, 1 by dou. So here we have 1 by r, dou r of Vr by dou r. Here we are differentiating with respect to r, and plus 1 by r dou V naught by dou theta, V theta by dou theta. Here we are differentiating with theta, and plus we have dou Vz by dou z, differentiating with respect to z. So this is the continuity equation where we are differentiating it with respect to r, theta, and z. So next, Laplacian is nothing but 1 by r, dou by dou r of r, dou pi by dou r, plus 1 by r square, dou square theta plus dou theta square, plus dou square pi plus dou z square. This is some complex equation where it occurred, again redifferentiating it. It is used in pressure and velocity diffusion terms. So this is some high complexity formula. Next we have Navier-Stokes equation in cylindrical coordinate. It is for axisymmetrical flow. We have dou by dou theta is equals to 0 and v theta is equals to 0. For continuity, 1 by r dou of r v naught r by dou r plus dou vz by dou z is equals to 0. So for axial momentum, we have rho or density. Rho is nothing but density. So rho of VR of dou Vz by dou R plus Vz of dou Vz by dou Z is equals to minus of dou rho by dou Z plus mu of delta square by Vz. So these are the terms of physics. Physical terms are more available here. This form is used for pipe flow and fully fully developed Laplacian flow. So now we will discuss about some application in fluid flow and pipe analysis. So first one is pipe flow. For circular pipes, it is basically particularly mentioned upon circular pipes. So cylindrical coordinates simply velocity profile parabolic, pressure drop calculations, laminar versus turbulent flow modeling. For fully developed flow, it will be VR is equals to 0, where rho Vz by rho Z is equals to dou Vz by dou Z is equals to 0. Here, the velocity depends on radius r. Next, we have pipe network analysis. Through network analysis uses algebraic equation, not differential. Cylindrical coordinates matter for head loss calculations, depends on pipe radius. Velocity distribution inside each pipe. Its Reynolds number is I is equals to rho Vd by mu. So here we have some physics terms here, but it depends upon the calculus part. Here d is equals to 2r directly from cylindrical geometry. So common formulas used here is Darcy-Weinbach formula, where it is HF is equals to H of LV squared by DUG, and Hagen-Poiseuille laminar, where delta P is equals to 8 mu L cube by pi r to the power 4. This equation comes directly from Navier-Stokes in cylindrical coordinates. Just now we have seen the Navier-Stokes equation in our applications here. by by applying these applications, we have discussed this formula. And why cylindrical coordinates are important. Best suit for cylindrical geometries like pipes, ducts, nozzles, and jets make Navier-Stokes equation simpler. Provide natural velocity components for spring rotation and also used in CFD stimulations of pipe flow. Essential for analyzing velocity distribution and pressure gradient. And we have next summary. So the summary for all the discussions we have. So we have discussed about cylindrical coordinates, where it defined with r, theta, z are used when flow has radial symmetry, and velocity expressed as vr, v0, vt tan vz, and continuity and momentum equations take simpler forms for pipe flow and used to derive pipe flow formulas using Hagen-Poiseuille velocity profile, and important in pipe network analysis for computing head loss, pressure variation, and flow rate. This is the summary, very short notes of the PPT. So once just recall the topics what we have discussed other than the summary, that are water cylindrical coordinates and rotational, circular or rotational symmetries, and we have discussed the relationship to the Cartesian and to the cylindrical coordinates, and velocity components we have discussed, and Navier-Stokes equation we have discussed, application in fluid flow and pipe analysis, and here we have a pipe flow and pipe network analysis, and common formulas we have discussed, that is Darcy-Weisbach and Hagen-Poiseuille. And Why cylindrical coordinates are important? We have just now discussed the topic. And finally, we have discussed the summary upon the coordinates and cylindrical cylindrical coordinates. Thank you.